quick show of hands, how many of you out here have ever built a machine learning model? Okay. And how many of you have put a machine learning model in production? It is actually inferencing on production data as we speak. Oh, okay, good. So there are a few of you. That's great. As Tarek said, my name is Labesh Patel. I'm the CTO and Chief Scientist at Jumio. A lot of my recent experience has been around productionalizing and building machine learning models. And today I'm going to be sharing some learnings from the trenches about the process of bringing about machine learning and AI in production. I'm going to briefly describe what we do at Jumio. This is to put in context the kind of data sets that we deal with, the restrictions that we have because of our compliance requirements like PCI and GDPR, and the resources that we have at our disposal that massively aid our machine learning pipelines. We are going to go ahead and formulate the ID verification problem because that's exactly what we do. And I'm going to then deep dive into a couple of the models. One is a classification model and one is a face match model. And hopefully we'll have some time left at the end of the talk for questions. If not, I'm around, just feel free. So Jumio is in the business of establishing trust online. As a lot of the current ways of authentication, such as passwords, SMS passcodes, and knowledge-based authentication have proven to be susceptible to attacks, businesses, governments, and a lot of regulatory authorities are looking for more robust ways of definitively establishing identity online. And Jumio uses a mix of ID experts and AI to verify the authenticity of an ID document, such as a state-issued driver's license, a passport, or any other national ID. This process plugs into your existing workflow to quickly authenticate an ID through a simple API call. The second solution that we have ensures that the person behind the transaction is actually present and is the same person that is on the ID document. This solution uses biometric facial recognition, ID experts liveness detection to match a selfie to the picture on the ID. We have customers, remote customer onboarding is a very common use case. Companies such as Airbnb, Coinbase, United Airlines use our solution. And if there are any workflows in the banking setup where you want to do a step of authentication, they would use some solutions such as ours. So let's try to formulate the ID document verification problem because that's what we need from an AI perspective. We need an X and a Y. So the X is the incoming document, which is the scan of a driver's license or a passport. And out goes one of the three results. It's either OK, approved. The ID is found to be non-fraudulent. The second tag is not readable. Now, an ID can be not readable for a lot of reasons. It can be blurry. There can be glare on the ID. So if we find that the ID is not readable, that's the tag that goes back. Or we explicitly find an attempt at fraud, in which case we would tag it as fraud and send it back to our business user. In addition to this, we go ahead and extract all the data that is on the ID, the first name, last name, the document number, the date of birth, all the information which is out there, and send it back to our business user. So this is the formulation of the problem. The reason why this is hard is because we accept traffic from all kinds of channels. So the mobile channel, where our business customer integrates with our mobile SDK, and their end user then just uses their mobile phone to take a picture of the ID and a selfie and send it over. Usually when images come in from the mobile channel, the image quality is reasonably good. The second channel that we support, and we still see a massive amount of traffic from this channel, which is the web channel. So users use webcams to take pictures of their IDs and they send them over. Now, webcams are notorious for poor quality images because there is no autofocus. And the image quality is completely variable. The third is a simple API call where you can upload anything. It can be flatbed scanners, mobile or web, and again, there is no guarantee of the image quality. So that creates a little bit of a problem. The other thing is that we support a lot of IDs. So all the IDs that you are seeing out here are just different variations on the California driver's license. And they have different templates, different security features, all the fields are in different places, and we support over 3,000 such IDs and subtypes. So any AI algorithm that we talk about needs to have a pretty broad understanding of every little security feature on every ID. Also, if you look at some of the sample images that come in, if we start looking at the top left image, that's how it looks when it just came in. It comes in at an angle. It can be any random angle. And the very first thing that we do is we use a mixture of a traditional computer vision model and an AI model to rectify it. Rectification is just aligning that image so that now the downstream steps have a better chance of extracting data or finding fraud. So in that case, once that happens, there is another AI model that kicks in, which looks at the blur on the image and figures out that, well, this image is blurry. We cannot really do anything with it, so it's going to go ahead and reject it as not readable. In the second case, the image set in the center, the same thing happens when the image comes in. We go ahead and rectify that image. And in this case, the text extractor is going to be able to extract the text, but there is another AI model which informs the workflow that, well, it is seeing glare, and the glare is not on a non-important random part of the image, but it is on a really important part of the image, which is the face of the person. So that is going to get rejected as not readable with a reason code of glare. In the third set of images, after the rectification, the text extraction works well. There is no blur, there is no glare, but then the orientation of the image of the person is wrong. So this is one of the security violations, and a fraud alarm rings. This image is going to be rejected as fraudulent because the person is supposed to be front-facing. So to reject an image is simpler because you're going through the steps, and any place where it fails, you can reject it. To approve it, every single thing for that particular ID needs to pass. So approval is a much harder process to automate than rejection. And furthermore, as we try to formulate any AI task, what you end up doing is you talk to your business partners. So in our case, I would go to, let's say, the chief of product and have a conversation, which typically goes like this. I'm like, okay, hey, Philip, we are trying to automate some of these things. And what is the conversion rate that you're comfortable with for non-fraudulent good users who are coming in? So at that point, Philip would take maybe 2 seconds to think about it, and he'll be like, well, we are actually in the business of converting strangers to customers. So we should have 100% of the good users pass through the system. And then the next question from me is, well, what is the appetite for letting some of the fraudulent users pass through our system? And even though the prior probability of fraud is only like 1%, Philip would think about it, and he would be like, well, we are actually in the business of finding fraud. So we really need to find all we cannot have any fraudulent users go through the system. So that's the identity verification nirvana, where you want to have all the good, normal, honest people trying to do business pass through, and you want to shut the gates on all the fraudulent users. So the business metrics are pretty stringent on this one. To maintain the matrix that are demanded by our business and honestly by our customers, we have a human-in-the-loop approach to machine intelligence. So an incoming scan goes through various AI models like blur detection, glare detection. A ton of models are looking at that scan. And if the rejection happens, that's fine. The scan gets automatically rejected. But at the end of it, all these results are collected, and they are sent to a human who does a sanity check on the results and either approves or rejects the image. So this formulation of collaborative intelligence that we have allows us to get industry-leading matrix in terms of conversion and the rate of fraud finding. The additional benefit that this has is anything that the human does is tagged and machine readable, and that informs our algorithms downstream. We are going to be deep diving into one of the models, but this is like the whole workflow of what happens to an ID. When the ID comes into the system, there is an acceptance model that just looks at the ID and decides whether or not to even accept that ID, and that's a machine learning model. The second is the rectification model that we talked about. It aligns the images. Third is the classification model, and we are going to deep dive into that, where that image needs to be classified into one of the 3,000 different ID types. The fourth is once we have the classification, we know the offsets of the different fields, we do a fuzzy field match, go ahead and do the data extraction, fraud checks, pass everything to the human for a sanity check, and that's the workflow. Now, let's zero in on classification. The problem formulation is pretty simple. ID comes in. After the rectification, we want to classify into one of the 3,000 distinct classes. Now, here you might be thinking, well, this is a lot of buildup for a pretty simple task, because image classification has been pretty much solved for the last few years. We can throw any model, take Inception version 4 or VGG 16, doesn't matter. You think you can start with a pre-trained network, remove the output layer, and instead of 1,000, go ahead and put 3,000, and this should be fine. Now, this is the happy ML workflow. This is what everybody wants, where the data is cleanly tagged. You have a workforce that can go ahead and tag incoming data. Your machine learning and AI engineers focus a lot on trying different machine learning models. They spend a lot of time on hyperparameter tuning, and then you go ahead and integrate and deploy. But what ends up happening is the problem is slightly different. So let's take an inventory of what we actually have. We have over 100 million tagged images, which we do. Now, for classification, the tags that we need are the granular tags, but the tags that we have in the system are aggregate tags. So for all the different California driver's licenses, the tag is going to say type driver's license, country, USA, still, state, California, right? Now, that creates a little bit of a problem because we need the granular classification if we were to go for one of the 3,000 different subtypes that we support. So that's a problem, but again, we do have a tagging team of human domain experts. So that is on the positive side. So this problem that started with an innocent classification problem now has morphed into a class discovery problem. Now we have to go ahead and discover the classes so that we can go ahead and do classification. And the ID volume distribution looks like this. I'll take a slight tangent and motivate this slide with a nerdy machine learning walk in the bar joke. So a machine learning algorithm walks into a bar and the bartender asks, "What will you have?" The machine learning algorithm answers, "What is everybody else having?" Right? So this is the problem you run into. Now when you query the database for, give me all the California driver's licenses, it's going to keep on giving you the same IDs, which are the majority IDs. And you are never going to be able to find the tail of the IDs through this process. So we need to do something to get all the classes. And here's where active learning comes to your rescue. Quick show of hands, how many people know what active learning is all about? Okay, so very briefly, active learning is a form of semi-supervised learning where the learning algorithm queries the teacher or the labeler for more informative samples as we go on. The formulation that we use is hybrid active learning because there is a step of unsupervised learning or clustering that is built in. And here's how this works. Now, this probably is the most important slide in the presentation because this is really key to understand how this works. So you start with a handful of classes, and you start with a handful of the most popular classes with labeled examples. And again, this is easy to get because as soon as you ask the DB for California driver's license, it's going to right away give you the most popular classes. So let's say out of the 3,000 classes that you have, very easily you are able to get your hands on the 50 most popular IDs, and you are able to get the data for those popular IDs, which is also easily available through our system by just simply querying it. Now what you're going to do is you are going to collect a statistically significant number of samples. In our case, it's about 3,000 to 4,000 samples per class. And you are going to now train a 50 class classifier in our case. And here, again, you can use any classifier. It doesn't really matter what network architecture it is. Pretty much the results are going to converge very quickly. At the end of this, what you will have is a classifier which is able to very confidently classify amongst these 50 classes. And you also output the confidence level that the classifier has when it puts a scan into one of those classes. Now you show a lot of unlabeled data to this classifier. It's going to very confidently go ahead and classify those 50 classes. And the classes where the items where it is less confident on, we are going to collect all of those in an other class. So the 50 classes, very confident, other class, everything else. Now we look at this other class, and we look at the feature vectors, which will be the output of any of the networks that you use, and you run an unsupervised clustering algorithm. You can use k-means or whatever you want, doesn't matter. And you will come up with clusters which form very nicely in this other class. Now you will have your human agents go and look into these different clusters, find the majority class within those, clean up those clusters, and now you have some more classes. So let's say we started with 50. After we did the first iteration, very quickly you might get another 25 or so. Now you go ahead and add these 25 to the initial 50, and now you start training a completely new classifier from scratch. You already have the labeled examples for the 25 that you just discovered, and now you have a 75 class classifier. And you keep on iterating this process till most of your volume is covered. Okay. So this is really important, and the workflow out here is also pretty self-explanatory as to what's happening. But anytime you have this issue where you are trying to look for something rare and you have a lot of unlabeled data, but you have some human experts, this is an algorithm that you can use, and we have this right now working for us. Now, once you have this model, you are going to create the service, create a RESTful API. If this is the very first time that you are putting this model in production, have a conversation with your data architect. There might be additional dimensions in your data warehouse that need to be added so that you can actually monitor the performance of something such as this. And if you have compliance regulations, you might want to add logging, monitoring, health checks to your containers, and you deploy it in the cluster. At this point, you might think that, okay, well, finally we should be done. We have a model in production. And it was supposed to be a simple model classification. Yes, there was a little bit of a hiccup. We needed to do class discovery, so we came up with this hybrid active learning, and now you put it in production. And you figure out that this is not the end of it, because the problem formulation is actually slightly different than what we started with. We are actually dealing with a scenario where the classes are dynamic. New classes keep on getting added all the time. So when you think of classification in a naive way, it's like you have a fixed set of classes, you have the model, and that's what you do. But when you put it in production, very quickly you realize that new IDs are coming in. But fortunately, since we are using hybrid active learning as the base infrastructure, this just gets seamlessly taken care of. So let's say when a new subtype comes in, the model is not going to be confident, it's going to go into that other bucket. And as the volume of this new ID builds up, a human agent can go ahead, look at it, figure out that, well, this is actually a new class, and then go ahead and kick off the retraining. So this just, hybrid active learning just takes care of this also. And another story from the trenches, a few months back, a new ID came in, a new subtype of an ID came in. The model was not confident. It went to a human agent, and the human agent promptly went ahead and rejected it as fraud. The reason was the country name on the ID was spelled wrong. The country is going to be unnamed. I'm not going to be calling out that country. But the ID, the country had the spelling of the country was wrong. Now, it seemed like a pretty rookie fraudster mistake. But what we saw is that a whole lot of volume of similar IDs started coming into the system. So we were like, okay, this fraudster probably sold his services to a lot of users, and all these users are using it at the same time. And when we investigated it further, it turned out this was not fraudulent at all. The issuing authority had given out a whole batch of IDs where the spelling of the country was wrong. And you cannot really pull it back, so it was out in production. And obviously, the system then knew about it. It became yet another subtype that we support. But things like that happen. Okay, so again, with the incremental learning, once you do that, you have that model. The way we productionalize a new model is you always have this champion model that is already in place. And when the new model comes in, we evaluate on the matrix of the new model, see how it is working with respect to the other model. And if it is better, we go ahead and refresh that model and switch it out. This also lends itself very nicely to the continuous improvement methodology, where using the same hybrid active learning infrastructure, we keep on harvesting more data and we keep on cleaning our data sets. So there is a lot of published research around this also, but in computer vision, the pipeline is very sensitive to the cleanliness of your data. It really pays to clean your data as thoroughly as possible. So the same hybrid active learning, when it is in production, when we see that the thresholds of confidence are low, we are going to go ahead and collect everything in another bucket. Humans go over it. There is an expert voting on any decision which needs to be reversed, and we keep on cleaning the database. Our target error rate that we want in our tagged data sets is 1/5 of the production target error rate. Now, what those exact rates are not important, but for the training data set, we don't want more than 20% of error that we can stomach for the production target error rate. And this works really well because we can keep on cleaning the data using the same technique of hybrid active learning. Also, very important note, probably a whole discussion in itself, is that we need to do all this in a PCI and GDPR compliant fashion. And for those who are not aware of what these requirements are, it suffices to say that whenever we hire a new person in our team, when they come across what they have to do to actually train a model, they almost get a heart attack. Because usual thing that you fire up your Jupyter notebook and you connect to your data, get it out. I am sure you're looking at your images and then targeting models. No, you cannot do that. You have to bring your training to the data instead of data to the training. Everything is behind a secure DMZ. And everything needs to be encrypted at all times. So if you are training models across several epochs, between epochs, everything needs to be encrypted. So you have to do a lot. A complete, there is no way to do justice on this topic in a few minutes, but it's doable. You can still be compliant to all these regulations and still be able to do machine learning and AI, and we do that on a daily basis. So the second case study that I want to talk about is face match. So the problem formulation, very simple. We have the selfie and we have the ID, and we need to match the person, the selfie to the ID. Now, most of the people are honest, so the data that we have, there is only about 1% fraud, and 99% are the same people on the selfie and the ID. And we have some biases on gender, ethnicity, and age. On the ID, we are able to get some more information like the age of the person, because if you look at any ID, there is the date of birth is there, and we know when the selfie is coming in, so you can really easily impute the age of the person. And the gender is usually listed on an ID. So that is another signal that you can use, which is not available in a traditional pure face match algorithm. Okay, so what is a possible approach out here? So one possible approach is, and this is very commonly used, you are going to crop out the faces from the selfie and the ID, and you are going to, and you can use a face detector. You can use a face detector from commonly used libraries, or there are very robust deep learning methods which are going to detect the faces, and then you can crop them. And then you're going to go ahead and train face embeddings using something like triplet loss. Anybody out here knows what triplet loss is? Okay, so very briefly, what triplet loss is you show 3 images to the network, and this network is a deep convolution network. The whole idea of this network is that it featureizes the face. So a face goes in, and it turns it into let's say a 512-dimensional vector. That is what the network is trying to do. And what you do during training time is you give it 3 images. The first image is the anchor image, and you'll get an embedding for the anchor image. The second image is an image of the same person as the anchor image, but a different image, so very similar. And you'll get an embedding of the similar image. And then the third image is a completely different person, and you'll get an embedding of this person also, of this face also. Now, what you are going to try and do is you want to maximize the Euclidean distance between the anchor image and the different image, different face, and you want to minimize the Euclidean distance between the anchor image and the similar image. And this is the objective that the network is given. So at the end of it, what you're trying to do is to train the network to find embeddings, features which are representative from a similarity perspective. And then you come up with a similarity threshold, and anything below that threshold is similar, anything above that threshold is dissimilar. And you can train these networks on public data sets. There are a lot of public data sets which are available for faces. And the initial approach would be, okay, well, let's just go ahead and train it on public data sets, and then maybe we can fine tune on the production data set. And we have millions of such pairs, and that would be a good initial approach. And it kind of sort of works. What ends up happening is that if you don't fine-tune it on your own data, it doesn't really work that well, especially when your metrics are, you want to find all the fraudulent users, and you want to make sure that all the good users are passed through. And your fine-tuning is really important. You have to fine-tune on your production data. But more interestingly, this whole concept of selecting these 3 images, the triplets, the model is extremely sensitive to that. So now, for most of the images, what ends up happening, the faces are so different that the model is just, without thinking, able to do that, so it doesn't learn much. So there is this formulation of training regimen called curriculum learning, where you give simple examples to the model to start with, and as it gets better, the examples, the training examples, become harder and harder over time. And this is what we need to do. But for that, we need to find those triplets. And this, again, lends itself very nicely into the whole active learning paradigm. So what we do out here is we go ahead and search for samples with matched faces, but where the model found a very low similarity score, and vice versa. This is going to be the hard positive regime. And the hard negative regime is you are going to be looking for samples where the faces are not matched, but the model found high similarity scores. So you keep on harvesting for informative samples, again, using the same active learning infrastructure. And this is not hybrid active learning, because here we don't have any unsupervised step. Everything that we have is completely supervised. And at any point, the model is there. You compute the model similarity and go through the pairs of approved ones, find the ones which are different, and go through the tagging team, and you keep on augmenting the data. So the same infrastructure, even the slide is pretty much the same, other than the fact that we remove that k-means step, and that works. So this technique of active learning just is incredible because it works through a huge slew of use cases. We saw that it worked in class discovery. We saw that it completely seamlessly solved the problem of dynamic number of classes, incremental learning. It was able to clean your data set on a routine basis. And now this is a completely different use case where you're trying to do face match. And as part of that, you realize that one part of the pipeline really needs clean data, triplets. And they are rare, the kind of triplets that the model needs to converge quickly. And we are using the same technique to find that. So extremely important in practice and in production. In summary, modeling is usually a very tiny part of what is required to get a model in production. And even simple problems like classification can turn out to be a multi-headed hydra when you actually go ahead and try productionalizing them. Because once you start looking at them, there will always be, if you're looking at any production data set, you will very rarely get a very uniform data set. You will have to use a lot of these techniques that need to go through, that you will need to go through to discover the classes, or the class labels will be dynamic, or you need to keep on cleaning. So very important to focus on active learning and master that. You want to keep on cleaning your data sets because computer vision is very sensitive to clean data sets, especially the problem of face recognition, extremely sensitive to a clean data set. If you have a clean data set, it only requires 15% of the initial data set. If that 15% is really clean, then that's all you require to get the same accuracy levels. And if your business matrix demand it, feel free to use collaborative intelligence or a human in the loop workflow. Initially, the tendency is to shy away from that, but just go ahead and espouse it because that allows you to, first of all, meet the business metric very quickly. And if you have your infrastructure set the way it should be, then anything that the human does can be used downstream by the algorithms to make your AI algorithms better. Finally, we are hiring. So we have R&D teams based out of Vienna, Austria, and we just opened an AI lab in Montreal. So if you're interested, please go to our website, reach out, and I'm here for questions. Okay.
How big is your data set you're able to collect for the loss use case?
We have over 10 million pairs.
So you said you started with a smaller set already. The clean data set for triplet loss, how big is that?
Oh, the clean data set for identity verification for the face match problem?
Yes, you said initially you started with a smaller one and you progressively make it harder.
So that was in the classification stage, yeah. So what you do in classification, our classification data set, the ID data set is humongous. It's over 100 million, right? So that initially we only start with about 2,000 samples per class. That's all you need. So you get the top 50 or so really popular IDs, and you only need about 2,000 or so per ID to start getting good results. Now and that's where collaborative intelligence also becomes important because the things that you count on, you cannot really count on in practice. So what I mean by that is we usually assume while training models that the labels are fine. But in reality, humans they are prone to error. And a model will come up with something and you would think it's wrong. Now, another human goes out and looks at that and it's like, no, the model was right. The human who tagged that ID did a mistake. And this collaboration, give and take, keeps on happening. And that's how the purity of the data increases. That's why we always have expert voting. We have 3 people looking at any time a label flip needs to happen. And it's not a majority voting. It's actually all 3 have to have consensus to flip a label.
How do you do the likeness test? If I have to do a selfie, I put some picture and then maybe close and see that.
So the way we have set up that is there is a ball that moves around in the mobile SDK, and the way your eyes follow the ball in the app is how we detect liveliness.
So if I follow the ID.
Yeah.
One of your earlier slides talked about bringing the model training to the data rather than vice versa. I was wondering if you could explain that.
Okay, so what happens with PCI compliance is that one of the regulations that we need to follow is the data cannot be used for anything other than the purpose of the data, right? So when a human looks at that image, that is the purpose of that particular workflow step, so that is allowed, right? But if now you want to train a model, right, and if you're sitting somewhere, and these locations which are already within the PCI DMZ, they are incredibly secure locations before any verification expert, or even when I go to that location, I am frisked like 50 times before I go into that location. They have nothing on them. They cannot have phones. They cannot have pencils, paper. They found a little piece of boarding pass on my back pocket, and I could not enter. I had to throw that away. So these locations are completely sterile. And now in those locations, the verification ID expert can look at the ID, right? Now, the locations that we have for doing machine learning and AI are normal offices. So even though there is VPN and firewalls and all that, that is like way not sufficient. You need a complete bomb-proof kind of a infrastructure for doing any processing from a PCI compliance. So if I get a AI engineer and he starts training algorithms, he cannot just, from his office cubicle, he cannot just get access to that data. So what you do is within the DMZ, the data is there. So you have we have our data on Amazon S3 buckets, and they are encrypted. And now when you want to do some training, what ends up happening is you go ahead and put your model out there without, and these, most of the time, the AI engineer is not even looking at the data. So they come up with some formulation of a model, and they put it out there within the DMZ. And the people who can look at the model are going to remotely supervise this process. And that's how it happens. And there are some things that you can do where if you want to get an image out of the PCI DMZ boundary, the image has to be completely obfuscated so that it is you cannot recognize what that ID is all about. So you can obfuscate that image, and then 3 different levels of people with different policies would look at that image, make sure that there is no leakage of personal data, and then that image can now come into a VPN location that an engineer can use. Now you can go ahead and train models which are so this image is not very representative of the actual image, very completely obfuscated, but you can still do machine learning on that to create the pipeline. Once you have the pipeline, you load it back, and hopefully it works better. If it doesn't, then somebody is going to remotely. So it's a very convoluted process. That's why it's a completely different topic as to how we do it. Yeah. Any other question? Yeah.
Well, I was actually I know this is very specific to the problem, but I was just wondering when you said that in active learning, the hybrid active learning, when you send it back to, what is the confidence level that you're usually looking for? Because you said that the models are very successful usually.
Yeah, so and this is something that comes from hit and trial, because it's part of the learning also, where you start with, let's say, 0.4, 0.5, 0.6. And the way we do it is for each of the class, there is a logistic on that. So it's a binary classification at each of the classes. So it's a multi-label thing going on. And then you look at that and say that, okay, well, is it over 70% confident, right? And if it is, fine. If it is not, then it's going to go into the other class. But even the ones where we classify it with high confidence, some sample of those would be checked by the humans to make sure that their confidence level is working. Questions? Good, thanks.